Today we want to look at some families of functions. And we're going to start with variations on e to the minus x squared. This is an important function to consider. This is the shape, this is commonly referred to as a bell curve. So this is the curve that lends its shape to the bell curve. And this is the shape of a normal distribution. Sometimes you'll refer to people taking some data and normalizing it. That is, looking at some data and imagining it looks like this. When students ask a teacher if they curve their grades, they think they're saying, do this. But when you ask me to curve grades, you absolutely do not want me to do this. You do not want me to imagine your grades as a normal distribution. First of all, there's not enough of you to do this. I have a large class at 50, and there is not enough of you to imagine a normal distribution. Students don't do this. Students tend to do this, where here are some A's and here are some D's. You do not want me to take this distribution and try to cram it into this one. But I realize that when you say, are you going to curve grades? You say, are you going to give us some free points? That's really what you're asking. So in future, rather than asking a teacher to curve grades, just ask, are you going to give us some free points? Because we know what this means. That's when students say, we think you're being kind of a dick, and we're hoping that our grades will be higher than these numbers reflect. So just ask it that way. You know what I mean? Don't try to sound fancy by saying, are you going to normalize our grades and make them fit the bell curve? Because the teacher would be like, oh, no, I'm not, because it won't. And second of all, if you just want free points, ask for free points. You know what I mean? I don't know why we got to try to hide what we want. So at the end of the semester, what'll happen is student will come to the office and say, oh, Leach, what can I do to pass this class? And if my first thought is, wait, who are you? That's a bad sign. Like if we're in person in class, like if you come up to me now, I haven't seen a student in person for, since last year in March. So that's different. But like in the before times, in the long, long ago, students would be walking up into my room, into my office at the end of the semester, like 2 weeks to go. And they're like, hey, what can I do to pass your class? I'm like, ooh, it's a bad sign that I don't know what class you're in because I haven't seen you for 3 months. I'm like, oh yeah, haha, I didn't like to go to class. I'm like, oh, I agree. It's kind of boring, isn't it? And I'm like, oh, well, what can I do? I'm like, well, next semester when you're taking this class over again, go. You know what I mean? Anyway, so let's talk about this. Let's make some observations about this particular function. It's important. It's a normal distribution. It's our bell curve. Let's make some observations. First thing that we want to notice is that it's symmetric about the y-axis. So there's an axis of symmetry. It looks the left side is a mirror image of the right side. So there's one observation that we can make. It's symmetric about the y-axis. Another observation that we might make is that there is a horizontal asymptote. No matter how large x gets, the function gets closer to 0, but never becomes 0. I can't take a positive number and raise it to any exponent and come up with 0. So we notice that there is a horizontal asymptote. So there's a horizontal asymptote. Horizontal asymptote where y is equal to 0. What that means is that the limit as x goes to infinity of e to the minus x squared is equal to 0. And that's also the limit as x goes to negative infinity. So that's what, in terms of limits, what we mean when we see there's a horizontal asymptote. It looks like for negative values of x, we see that the function is increasing. So f of x is increasing when x is 0. Or sorry, when x is less than 0. E to the negative x squared has a local maximum at x equals 0. And e to the minus x squared is decreasing after x equals 0. Since f of 0 is equal to 1, it has a local maximum of 1. When x equals 0. So we notice that the function is increasing when x is negative, is flat when x is 0, and then decreasing when x is greater than 0. It also looks like we're going to have two inflection points, because here we see the function is concave up. In this middle part, it's concave down, and it's concave up again after this middle part. So it looks like we have two inflection points. So that's interesting. We've got the one critical point and two inflection points. It's hard to pinpoint where the inflection points are. But they're about right there. And because the graph is symmetric, we expect them to be at the same, at opposite x values. So there's a lot we can get just by looking at the graph. We notice the symmetry. We can think about why that is. We have this horizontal asymptote at y equals 0. We see the function increasing, a local maximum, and then decreasing, and we see these two inflection points. These are just observations based on things that based on looking at the graph. We should justify all this stuff. So take a moment and think about what it is about this function e to the negative x squared that'll make it symmetric about the y-axis. What is it about the function that gives us this horizontal asymptote at 0? How can we verify that there's this one critical point at 0? And how can we find these two inflection points? Those are 4 observations that we made. Let's come back to these 2 that have to do with the function and take a look at some of the calculus stuff. This is a calculus class after all, and we have just been doing this thing with the derivative, set it equal to 0, and solve. So let's find the critical points. So if f of x is equal to e to the negative x squared, let's find f prime of x. The derivative of e to the negative x squared is e to the negative x squared. And we have to multiply by the derivative of the inside because of the chain rule. So the derivative of minus x squared is minus 2x. I'm going to write the minus 2x first because otherwise I'd have to use parentheses and I'm in danger of making it look like two terms when it is in fact two factors. If we want to talk about the critical points, we'll set this equal to 0 and solve. And this will only have one solution. Just like we suspected, we only get the critical point at 0. Notice that e to the negative x squared is never equal to 0. So the e to the negative x squared factor is never 0. E to the negative x squared is never 0. That's why we never see this graph cross the x axis. And that's one of the things that explains this horizontal asymptote behavior. As x goes to infinity, we're taking e to a very large negative number. So e to the negative x squared is never equal to 0. It's just going to get smaller and smaller. So yeah, go ahead.
Function, please. On the function here, we have e to the negative x to the power of 2. On the f prime, the first derivative, then you set up to 0. And then we have 2x equals 0. And then x is 0, the critical point. So where is this critical point at? The x equals 0?
It's x equals 0. There's a critical, f has a critical point at x equals 0.
If it's on the graph, where is that?
What was the question again?
The very last f prime of x, and then we have the answer on the right. X equals 0 is the critical point. If we look on the graph, is that 0 somewhere on the graph that you draw?
Yeah, it's on the x-axis when x is equal to 0. There's the critical point.
Oh, okay.
So just like we suspected, the function goes flat at that point.
Oh, so that is the 0 point.
Yeah, right. No, that's the critical point.
Oh, that's the critical. Oh, okay.
That's the critical point of the function.
Right. But it's never approached to 0. It cannot be 0.
Okay. What never approaches 0? Don't say it.
Oh, sorry. Thank you.
Don't use the word it because we're referring to a lot of things.
Horizontal. Got it.
Yeah.
Thanks.
So the function never equals 0. E to the negative x squared, this factor is never equal to 0. We can't raise e to some number and come up with 0. The only way to get to 0 is through multiplication by 0 or adding an opposite. Can't get there through exponents. So there's other things that we see. We see that the function in the graph, we can see that the function is increasing when x is less than 0 and decreasing after that. So if I draw a number line with my critical point on it, I'll draw my number line x with my critical point when x is equal to 0, f prime is equal to 0. And so this is dividing the number line into two halves, the below 0 and above 0. So if I pick a value of x that's less than 0, like -1, then f prime is -2 times -1 e to the -1 squared. And the -2 times -1 is going to be positive. So this is positive. F prime is positive when x is less than 0. Similarly, if I plug a value of x that's greater than 0, like 1, I will find that f prime of 1 is negative. So I can see that the function is flat at 0, is increasing before and decreasing after. So that means we have a local maximum at 0, just like we suspected. Remember, doing this calculation was not about finding the critical point and determining it was a local maximum, but making sure that the calculus matches up with what we are observing about the function. All right. We also note that there are we also see that there must be 2 inflection points on this graph. So that must be 2 points where the second derivative is equal to 0. Let's find out what happens if we look for f double prime. For f double prime, the second derivative is going to require a product rule because I've got -2x times e to the minus x squared. So now we have to do the product rule. The product rule says take the derivative of the first times the second plus the first times the derivative of the second. So here we are using the product rule. We need to use the product rule to find f double prime. Since we're going to be working with this function, now if you're just typing a quiz, this would almost be okay. I really don't like that -2x times another -2x, but let's clean this up a little bit. If you're doing a quiz, -2 e to the minus x squared minus a minus is plus 4x squared e to the minus x squared. That would be perfectly acceptable for a quiz answer. Since we're working with it, it's going to be useful for us to factor out the e to the minus x squared. And while we're at it, I'm going to factor out the -2. So I have -2 e to the minus x squared times 1 plus 2x squared. And I spelled minus wrong. 1 minus. I was even thinking to myself, if you factor out the negative, don't forget that change the sign. My brain went all teenager on me and said, well, yeah, I'm listening. And then what happened? I didn't factor out the negative. If we're looking for inflection points, and we are, if we set the second derivative equal to 0, we can see that we're going to get the 2 inflection points. So if we set the second derivative equal to 0, e to the negative x squared is never 0. But this 1 minus 2x squared could be 0. And it's going to have 2 solutions. And they're going to be opposites of each other. So x is going to be plus or minus, just like we suspected, the square root of a half. So I'll subtract 1, divide by -2 to get x squared equals a half, and then take the square root for a plus or minus 1/2. Just as we had suspected, there are two inflection points, and they are in fact opposites of each other. They had to be. We know the graph is symmetric. Speaking of the symmetry, this result also highlights why the graph is symmetric in the first place. When we look at the equation e to the minus x squared, all the inputs get squared. The first thing that happens to them is that all the x's get squared. All the negatives become positives. So the reason that we get symmetry about the y-axis is the x squared. The x squared part is why we're going to get that symmetry about the y-axis. Negative 2 squared is positive 4. 2 squared is positive 4.
For first knowledge, you don't mind on the very bottom step, we have x equal plus minus square root 1/2. On above it, how do you get to that? We have above that we have 1 minus 2x squared equals 0. And
So
how
if
you
we have 1 minus 2x squared equals 0,
less
I can add the 2x squared to both sides, divide by 2, and then take the square root.
Okay. Thanks for first knowledge. Thank you.
Any other questions? All right. So the calculations match up with what we observed on the graph. And there are always reasons for the things on the graph, in the equation for the things on the graph. The symmetry about the y-axis is because the x is being squared. So all the negative x's look like the result of positive x's because the negatives get squared away. Even exponents don't respect negatives. They make all the negatives positive. Even exponents are your friends that are like, oh, hey, cheer up when you're sad. And try to explain to you like why you shouldn't be sad. As if that's any of their business. You know what I mean? The horizontal asymptotes. As x goes to infinity, e to the minus x squared will go to 0. Because we're just taking e and raising it to a larger and larger negative exponents. So it's like a 1 over e to the x. And since e to the x is going to infinity, 1 over e to the x is going to head off towards 0. So it makes sense that we get those horizontal asymptotes. We see that there's only one critical point on the graph. There's only one local maximum. And the calculations tell us that as well. We only found one critical point, and it was a local maximum. Although the inflection points are harder to see just by looking at the graph, or harder to pinpoint, we definitely know they're there because we could see clearly concave up, concave down, and then concave up again. So there must be two inflection points. Because if we go to concave up to concave down, back to concave up, it changed, the concavity changed twice. There must be two inflection points, and we found them. We're just trying to make our calculations match up with what we've observed about the function.
Another question, please, Professor Lee. So when I use my calculator, square root 1/2, I have like 0.70.
Yeah,
So is that the critical point? Oh no, that's it. Where is that on the graph? Where is that? Oh,
those
it's
are,
mean it never approaches 0. Is that what it means?
no, it means those are the inflection points. Those, we got the plus and minus 1/2 from setting the second
Oh,
derivative equal to
I got
0.
okay. The positive and then negative. Thanks. Thank
Yeah.
you. Clarify. I see it now.
So on the graph, here's the positive square, positive 0.7, here's negative
Yeah, yes,
0.7.
correct. Makes sense. Thank you, Professor Leach.
Let's look at some variations on this graph or this function. So let's look at some variations. Let's build this generic function, f is equal to, oops, f of x. And I forgot what I called each piece. I went with the standard trig versions. So let's say d plus a times e to the negative b times x minus c squared, where a, b, c, and d are constants. Let's make some observations about what happens if we start messing around with these values of the constants. So let's switch over to the board, or sorry, let's switch over to the graphing calculator. There's the graphing calculator. So taking a look at the graphing calculator, I started off with just the baseline e to the minus x squared. And so that's the blue graph shown here. It's a little bit darker blue than I have on the notepad. But let's turn on my variation. Now, my variation is going to be sitting right on top of my original. So in the variation where I have d plus a e to the negative b times x minus c squared, the default is d equals 0, a is equal to 1, c is equal to 0, and b is equal to 1. So we know that there's our local maximum. I don't think this finds inflection points for you. No, we know that there's an inflection point here at 0.7071, but it's not going to let me just mark that point. But imagine there's the inflection points at plus and minus 0.7071. Now, what we want to do is think about what happens if I start adjusting these values of A, B, C, and D. And then we want to think about what do A, B, C, and D have in common and what's different. Because I've broken this up into my 2 and 2. There's 4 things going on. And so we're going to have 2 different categories with 2 choices in each one. All right, let's see what happens if I change the value of D, since that one's just listed first. So if I increase the value of D, notice that the shape of the graph is not changing. The shape of the graph is maintained. The graph just shifts up and down. So just by moving the value of D up and down, we're shifting the graph up and down, but we're maintaining the shape of the graph. So D shifts the graph up and down. And what we're doing, we're maintaining the shape. Nothing is getting stretched or squished. We're just moving the graph up and down. Oh, I don't have enough window. Comes through and then disappears. So if we watch D go back and forth, we can see the graph moving up and down. Let's see what happens if we adjust the value of A. So as A increases, notice that the horizontal asymptote stays the same, but the local max moves up and down. And if A goes negative, that flips the whole graph over. So A moves the graph up and down. It doesn't seem to change the location of our inflection points. It moves the local maximum up and down, but it doesn't seem to change where the horizontal asymptote is. So A seems to move. So what's happening is that the graph is getting stretched vertically. So it's stretching the graph up and down. We're not moving anything. The horizontal asymptote stayed where it is. Maintained the horizontal asymptote. Let's see what happens if we move on to the value C. So that's just next. I'm going to start changing the value of C. Notice that what's happening is that the graph is maintaining its height. It's just shifting where the local max happens, left and right. So what's happening when we change the value of C is that the graph is shifting left and right, but maintaining its shape. Notice that the shape stays the same. Any questions?
Yes, Professor Rich, quick question. On the top, we have y, the function e equal to oh, what happened? Oh, I'm sorry, the function y equal to e negative x to the second power. So the second derivative, we set to 0, then we have plus minus 0.7.
Well, we've moved on from the second derivative. We're just looking at variations of the graph.
Oh, just one quick question. Quick professor, on the first prime, the first derivative.
We've moved on from that. We can talk about this in office hours.
Thanks,
But
Professor.
I'm talking about variations on the function now. So when I have to change the value of C, we're shifting the graph left and right. We're shifting the graph left and right, but maintaining the shape. And so finally, if we look at what happens when we change the value of B, we increase the value of B. Notice that the top stays where it is. The maximum stays where it is. And what's happening is that the sides are getting pinched in or pulled apart. So what we're doing is creating a horizontal stretch of the graph. So the value of B stretches the graph horizontally. So it's stretching the graph horizontally. There's not any vertical changes. The high point is still the high point. The asymptote is still the asymptote. But we're stretching the graph horizontally. no vertical changes. So we're maintaining the horizontal asymptote. So we had these 4 different values included in the function in different ways. Different operations, addition and multiplication, and they occurred at different times, and they had different changes, shifting and stretching, and then there's vertical changes and horizontal changes. So we want to organize these changes. We'll talk about that next week on Monday. We'll organize these 4 different kinds of changes. All right, well, that's going to do it for today. That's going to do it for this week. I'll see y'all on Monday. Everybody have a good day. Have a good weekend. And thanks for playing.